Momentum. Chapter 6, momentum. We have momentum is the product of mass and velocity, right? The equation we use, mass times velocity equals momentum. We use the letter P to represent momentum. M is mass and V is velocity. The unit that we have here is, if mass is kilograms and velocity is meters per second, we have a kilogram times a meter per second. Right? Yeah.
Alright. That's the only thing that, when we do all those, like, how do we get those? What I usually get confused.
All right, energy was a scalar quantity. Momentum is a vector quantity where direction matters. And because it's a vector quantity, we're going to be using trig functions to find the components, x and y components. First question, what is the momentum of a 3.5 kilogram medicine ball traveling 4.3 meters per second north? So we just use this simple equation here. All right, so we have momentum is mass times velocity. We have a mass of 3.5. We have a velocity of 4.3 meters per second north, which, would that be positive or negative if we go north?
Positive.
Positive, all right. So if we're using a traditional coordinate system, we have north is positive and south is negative, east is positive, west is negative. So you could have this as positive 15 kilograms times meters per second, or we could say 15 kilograms times meters per second north. Easy, right? Easy peasy. Impulse momentum theorem. All right, so we have this thing called an impulse. What you just learned about that equation, that momentum is mass times velocity, is called linear momentum. It's instantaneous velocity. All right. Impulse momentum, this deals with a change in momentum. All right, so we took a velocity that was an instantaneous snapshot of that velocity. It was that velocity at that moment, right? Mm. Now we have a change of velocity, which is a beginning and a final velocity, and what the difference is between the two of them. Mass is still mass. This thing is impulse, is that if a force is applied to an object, what happens to the object?
It moves.
So forces cause acceleration, right?
Yeah.
So you have a change in velocity. Whenever a force is applied, you have a change in velocity. So what's happening here is a force applied for a specific time period will give you a specific acceleration or change in velocity during that period. When the force stops being applied, the acceleration stops. The velocity doesn't stop, but the acceleration stops. So this is what we call an impulse. And in New York State Regents, they use the letter J. If you have New York State Regents reference table, for some ungodly reason they decide they're going to use J for impulse so that it's different. Most textbooks use an impulse as delta P. It's a change of momentum. So this is delta P, that's delta P. Either one of them is equal to each other, so obviously they're the same thing. Mm-hmm. You don't have to use two different letter variables like J and P, because if it's the same thing, you could use the same variable. A net force multiplied by the time, or a net force that's applied over a time period causes a change in velocity, which is known as a acceleration. Right? If we're looking at momentum, which is mass times velocity, linear momentum is mass times velocity. A change in that velocity gives you a change in that momentum, right? More velocity, more momentum. Mm-hmm. Yeah. All right. So what we have here is where we come up with this idea that these are the same things. All right. Newton's second law is force equals mass times acceleration, which is what I was getting at just a moment ago. And acceleration is a change in velocity over a change in time period. Simple kinematic equations that we used already, which means that if we have this force equals mass times delta V over delta T, and we multiply this side by delta t, and then multiply this side by delta t, then these cancel out. You have m delta v, f delta t, and we see that right here. So we already knew this. You know, if I didn't tell you this today, and I told you momentum was m change in velocity, you should already have been able to take your 2 chapters ago equations and formulate this into that it's the same thing.
I get that.
Right? So here we go. A 1,320 kilogram car traveling at 40 meters per second. 68 kilogram passenger applies the brakes for 8.5 seconds to bring the car and himself to rest. What's the velocity at rest? 0. All right. Find the average force the seatbelt must exert on the person over this time period. Right? 8.5 seconds. So we're looking for force. We're looking for the force. We know the time period. We know what t is. We know the change in velocity. It's from 40 to 0. And we know the mass of the car. Mass is the mass of the person and not the mass of the car. So we have our equations. Force times the change in time equals mass times the change in velocity. So the force we're looking for is the mass times the change in velocity divided by the change in time, the time period. And we put our numbers in there, and we get an answer. All right. Suppose that the time was 0.12 seconds instead. Wow. Yep. So what we end up with is a very large force. So here we come up with this whole concept that, like we did the egg drop. The larger the time period that force,
The less work, or the less.
yep, you get the same change in momentum. All right, so the larger the time period, the smaller the force. The smaller the time period, the larger the force. So if you drop an egg and you want the egg to not break, you want it to have as little force as possible. You want it in this impact. You want it to have a long crumple period, or a long time that it hasn't dropped before it stops the ground. All right, got it? Good. All right, 255 gram ball traveling at 12 meters per second to the right hits the wall and rebounds at 12 meters per second to the left. If the ball contacts the wall for 0.18 seconds, find the force of the wall on the ball.
So wall, ball, wall.
Ball, wall.
All right. So
And there it is right there.
So it's 0.255 kilograms. Right.
Yep, first thing is we have to convert it to, our mass has to be in kilograms.
So there's no change in velocity. Well, there is. It goes from 12 to 0 back to 12.
Excellent, goes from 12 to 0 to back to 12. So remember I was just alluding to this, what was it that?
Direction. So it'd be traveling in a negative direction, right?
Good. So we have a positive, all right, we have positive 12, and we have negative 12. So our differences between the two, we see that we have a negative minus a negative, or we have a positive minus a minus, which makes a plus.
Mm-hmm.
So in either situation, what we're doing here is we're adding this together. But our answer here is negative 34 newtons. Because the force is in the opposite direction of the original motion.
Wait, so why is the first one negative? On the second one?
It's final, or change, delta V equals V final minus V initial, right? What's our initial velocity?
12.
Plus.
Yep.
What's our final velocity? Minus?
Oh, yeah,
Minus,
final goes
minus.
for initial. Yeah.
Yep.